When we stare into the night sky, we tend to think we see the universe as it truly is, bright points of light, distant galaxies, and faint nebulas stretching as far as our telescopes can reach. But what if I told you that the cosmos has been holding up a giant, invisible, magnifying glass for us this entire time? A lens not made of glass or plastic, but forged from the raw gravity of galaxies, galaxy clusters, and even the mysterious dark matter that shapes our universe. This is gravitational lensing, one of the most breathtaking predictions of Albert Einstein's general theory of relativity, and today, we are going to uncover its full story, how it bends light warps, space-time reveals, hidden galaxies, maps, invisible mass, and helps us answer some of the biggest questions in all of cosmology. This is not just a weird cosmic quirk. It is humanity's most powerful tool to peer deeper into space and time than we ever thought possible. Let us start at the very beginning, over a century ago, when our entire understanding of gravity was turned upside down. For hundreds of years, we lived by Isaac Newton's vision of gravity, a force that pulls objects together, acting instantly across empty space. Newton's laws worked beautifully for falling apples, orbiting planets, and even sending rockets to the moon, but they could not explain one critical thing: how light behaves under extreme gravity. In 1915, Einstein changed everything with his general theory of relativity. He did not just describe gravity as a force. He redefined it as the curvature of space-time itself. Imagine space-time as a giant, stretchy sheet spread across the universe. When you place a massive object like the Sun, a galaxy, or a cluster of thousands of galaxies on that sheet, it does not just sit there, it presses down warps and curves the fabric around it. Any object, including light, that travels near this massive body will not move in a straight line. It will follow the curved path of the space-time itself. That is not just a theory. That is the rulebook of our cosmos. At first, even Einstein himself was unsure if we could ever observe this effect in action. In 1912, he did the math and realized that a star could bend light from a more distant star, but he thought the effect would be far too tiny for our telescopes to detect. He even called it essentially useless for observation. But the universe had other plans. In 1919, a team of astronomers, led by Arthur Eddington, set out to test Einstein's wild idea during a total solar eclipse. The idea was simple: when the moon completely blocked the sun's bright light, they could photograph stars that appeared near the edge of the sunday. If Einstein was right, those stars' light would be bent by the sun's gravity as it passed by, making the stars look slightly shifted in the sky compared to their normal positions. On May 29, 1919, two expeditions traveled to Principe Island in West Africa and Sobral, Brazil, to capture the eclipse. When the results came back, the stars were exactly where Einstein's equations predicted they would be. The headline around the world screamed, "Revolution in Science, New Theory of the Universe, Newton's Ideas Overthrown." That single experiment proved that gravity bends light, and it planted the first seed of gravitational lensing. But it would take decades for astronomers to realize just how powerful this effect could be. In 1937, a brilliant astronomer named Fritz Zwicky made a bold leap. He argued that Einstein was too modest, individual stars were too weak, but entire galaxies and galaxy clusters were millions of times more massive. These cosmic giants could act as full-scale lenses, bending, distorting, and magnifying light from objects billions of light-years behind them. Zwicky said gravitational lensing would let us see galaxies so far away they would otherwise be completely invisible, and it would let us weigh cosmic structures to measure their total mass. At the time, almost no one listened to him. His ideas were seen as too radical, too far ahead of the technology of his era. But Zwicky was right, and decades later, his prediction would come true in spectacular fashion. The first true gravitational lens was finally discovered in 1979, more than 60 years after Einstein's prediction, and 40 years after Zwicky's bold claim. Astronomers were studying a quasar, an extremely bright, distant core of an active galaxy named Q0957+561. To their shock, they found not one, but two identical quasars sitting side by side. They had the same brightness, the same spectrum, the same redshift, everything. It was impossible for two separate quasars to be exactly alike. The only explanation was that a faint, unseen galaxy between Earth and the quasar was bending its light into two separate images. This was the first confirmed gravitational lens, and it proved that Zwicky's cosmic magnifying glass was real. Since that day, astronomers have found hundreds of gravitational lenses across the sky, ranging from small, subtle distortions to jaw-dropping perfect rings of light that look like they were carved by a cosmic artist. Now, let us break down how gravitational lensing actually works in simple terms that anyone can understand. There is no complicated math here, just the amazing behavior of light and gravity. First, you need three things: a distant light source, like a young galaxy or a quasar, a massive foreground object, the lens like a galaxy or galaxy cluster, and us, the observers here on Earth. When light from the distant source travels toward Earth, it passes right next to the massive lens object. The lens's gravity warps the space-time around it, so the light takes a curved path instead of a straight one. Depending on how perfectly the source lens and Earth line up, we see different kinds of lensing effects. Astronomers group them into three main types: strong lensing, weak lensing, and gravitational microlensing. Each one gives us a different window into the universe. Strong gravitational lensing is the most dramatic and visually stunning kind. It happens when the alignment is nearly perfect and the lens is extremely massive, usually a dense galaxy or a huge cluster of thousands of galaxies. In these cases, the light from the background object gets bent into multiple images, long stretched arcs, or even a complete circle called an Einstein ring. An Einstein ring is one of the most beautiful sights in astronomy. A perfect glowing circle of light around the foreground lens, created when the source lens and Earth are almost exactly in a straight line. The James Webb Space Telescope and the Hubble Space Telescope have captured dozens of these perfect rings, some from galaxies over 12 billion light-years away. These arcs and rings are not just pretty, they are cosmic clues. By measuring how curved these arcs are, astronomers can calculate exactly how much mass is in the lens object, including the mass we cannot see. Weak gravitational lensing is much more subtle. It does not create obvious rings or multiple images. Instead, it slightly distorts the shapes of thousands of background galaxies, making them look a little stretched or sheared. We cannot see this distortion with our eyes, but with powerful computers, astronomers can analyze the shapes of millions of galaxies across the sky and map the gentle curvature of spacetime caused by invisible mass. Weak lensing is now our best tool to map the large-scale structure of dark matter across the entire universe. Dark matter is the invisible substance that makes up about 85% of all matter in the cosmos. It does not emit, absorb, or reflect any light, so we cannot see it directly. But gravitational lensing lets us see dark matter by the way it bends light. It is like looking at a shadow and knowing exactly what object is casting it. The third type is gravitational microlensing, which happens when a relatively small object, like a single star or even a planet, passes in front of a more distant star. The gravity of the foreground star briefly magnifies the light of the background star, making it temporarily brighter without changing its color. Microlensing has become one of our most effective methods to find exoplanets, including small rocky planets that are hard to detect with other tools. It has even helped astronomers find isolated black holes drifting through the Milky Way, completely invisible except for their microlensing effect. Every time we see a tiny brightening of a distant star, we might be witnessing a planet or a black hole we could never have found any other way. Let us talk about why this matters, why gravitational lensing is not just cool space art, but a revolution in cosmology. First, it acts as the universe's natural telescope, magnifying objects that are way too faint and far away for our most powerful machines to see on their own. Some distant galaxies are magnified by factors of 10, 20, even 100 times by gravitational lenses. Thanks to this, we have observed galaxies that existed just a few 100 million years after the Big Bang, when the universe was still in its infancy. These are the earliest building blocks of galaxies, like our Milky Way, and without gravitational lensing, we would never know they existed. Second, gravitational lensing is the most accurate way we have to measure dark matter and its distribution. When astronomers calculate the mass of a galaxy cluster using the motion of its galaxies or the heat of its gas, they get one number. But when they use gravitational lensing to measure the total mass, including dark matter, they get a much larger number. The difference is, the dark matter and lensing lets us map its location with incredible precision. This has confirmed the leading theory of cosmology, the lambda CDM model, which says our universe is made of normal matter, and dark energy. Without gravitational lensing, we would not have solid proof that dark matter is real. Third, gravitational lensing helps us measure one of the most important numbers in cosmology, the Hubble constant, which tells us how fast the universe is expanding. By measuring the time delay between the multiple images of a lensed quasar light takes different paths around the lens. So one image arrives a little later than the other. Astronomers can calculate the exact distance to the quasar and the expansion rate of the universe. This method is independent of other techniques, making it critical for solving the ongoing debate about the universe's exact expansion speed. Over the past few years, the James Webb Space Telescope has taken gravitational lensing science to a whole new level. Webb's infrared vision can see through dust and capture the faintest light from the most distant lensed galaxies. In 2025 and 2026, Webb captured several nearly perfect Einstein rings, including one from a galaxy 12 billion light-years away, allowing astronomers to study its molecular makeup and star formation history in detail. These observations are rewriting our understanding of how galaxies formed and grew in the early universe, and they are giving us new clues about dark matter and dark energy. Every new lens Webb finds is a new window into the earliest moments of the cosmos. What makes gravitational lensing so special is that it connects the smallest, most elegant equations of physics to the largest structures in the universe. It started as a thought experiment in Einstein's notebook, was proven correct during a solar eclipse, was ignored for decades, and is now the foundation of modern cosmology. It is a reminder that the universe is full of hidden tools waiting for us to discover them. Tools that let us see what was once invisible, measure what was once unmeasurable, and answer questions we once thought were impossible to solve. We are only beginning to unlock the full potential of gravitational lensing. Future space telescopes, like the Euclid telescope and the Nancy Grace Roman telescope, will survey billions of galaxies to find millions of new gravitational lenses. These missions will create the most detailed map of dark matter ever made, measure the universe's expansion with unprecedented precision, and find thousands of the earliest galaxies in the cosmos. Gravitational lensing is not just a chapter in the history of astronomy. It is the key to the next era of space exploration. Please like, comment, share, and subscribe to the channel.